Okay, have you ever stopped to think about what squeezing a simple rubber ball could possibly have to do with your high-tech air conditioner? I know, it sounds a little out there, but the answer connects some super simple physics to the smart tech that, keeps you cool. Let's get into it.
Yeah, I know, it's a strange question, but stick with me because the answer is actually fascinating. It's all about how these forces we can literally feel in the world around us are harnessed by these invisible principles that power all our gadgets. And trust me, by the end of this, you're going to see exactly how these two completely different things are connected.
Okay, so first things first. Before we get to the cool tech, we got to get a handle on two really basic ideas: force and pressure. And don't worry, we're not going to break out any complicated formulas here. We're going to do this with stuff you can probably find lying around your house.
So, just imagine this super simple action. You're squeezing a rubber ball in your hand, right? You're applying a force, and you can see the result instantly. The ball's shape changes. It kind of squishes down. Then you let go, the force is gone, and poof, it snaps right back to its original shape.
And that is the absolute key takeaway here. A force is just a push or a pull. That's it. And it can change an object's shape. It's really the most basic way we interact with the world, and you're about to see just how powerful this simple little idea can be.
All right, now let's add a little twist to this. Imagine you've got a block of clay. You take a sharp knife and a flat, blunt ruler, and you push both of them into the clay using the exact same amount of force. So what happens? I mean, you already know the answer, right? Your gut tells you that knife is going to sink in way, way deeper.
In this experiment, well, it perfectly illustrates the concept of pressure. See, it's not just about how much force you're using, it's about how much area you're spreading that force over. The knife funnels all that force onto one tiny, sharp edge, creating a ton of pressure. The ruler just spreads it all out. And believe me, that difference is everything. Okay, so we've got a handle on the forces we can create ourselves, right? Squeezing a ball, pushing a knife. But what about the forces that are always pushing on us, even when we're just standing still? Turns out, one of the most powerful forces is completely invisible, and it's all around us right now. It's the pressure of the air.
You've probably seen this one before. It's a classic experiment that honestly feels like a magic trick. You take a glass, you fill it all the way to the top with water. Then you put a flat piece of cardboard on top. And then you take a deep breath and you carefully turn the whole thing upside down. Now, everything your brain knows about gravity is screaming that water should come pouring out, right? I mean, the card is flimsy, the water is heavy, and yet it just stays there. So what's going on? What invisible force is strong enough to just defy gravity right in front of our eyes?
It is the incredible power of atmospheric pressure. The air in the room, the very air we're breathing, is pushing up on that card with more force than the water is pushing down. It's wild to think about, but we're basically living at the bottom of a giant ocean of air, and the weight of all that air is easily strong enough to hold that water up.
So you want to see just how strong this air pressure really is? Try this. Take an empty soda can, put a tiny bit of water in it, and boil it. Once it's full of steam, you seal it up and then quickly cool it down under some cold water. That steam inside condenses, creating a vacuum, and the result? Bam! The can just gets instantly violently crushed. And get this, that's not something happening inside the can. That is the pressure of the outside air, the same air that's all around us. That's what's doing the crushing. It is an absolutely mind-blowing demonstration of these powerful unseen forces that are just always at work.
Okay, so we've seen how powerful these physical forces can be. They can crush a can. But how do we actually use a physical property, like say a change in temperature, to control something electronic? Well, the answer is in this tiny but totally brilliant little component that acts as a bridge between the physical world and the world of electronics. So say hello to the thermistor, and honestly, the name pretty much tells you everything you need to know. It's a mashup of thermal, which means heat, and resistor. And that's exactly what it is. An electronic resistor whose resistance, how much it fights against electricity, changes in a really predictable way depending on how hot or cold it is.
Now these thermistors, they come in two main flavors. You've got NTC thermistors and PTC thermistors. Think of the NTC type like this. The hotter it gets, the less it resists, so more electricity can flow through. It's like opening a gate. The PTC type does the exact opposite. It resists more as it heats up, closing the gate. For our smart fan project, we're going to focus on the NTC one.
All right, enough with the theory. Let's get to the fun part. Let's see how this tiny little component can actually be the brain of a simple automated circuit. We're about to put together a system that can react to the world around it, completely on its own.
And our goal here is super straightforward. We're going to build a smart fan. A fan that knows when it's getting hot and turns itself on, and then knows when it's cool enough and turns itself off. No buttons, no switches you have to flip. It's going to be purely automatic, all based on the temperature in the room.
Okay, let's start the scene. The room is nice and cool. Our NTC thermistor is also cool, which means its resistance is super high. It's basically acting like a closed gate, blocking electricity. Because of that, this other little component, a transistor, which is basically just an electronic switch, stays turned off. And if the switch is off, well, the fan is off. Simple as that. But now, let's say the temperature in the room starts to rise. It's getting warm. As our thermistor heats up, its resistance drops. A lot. Suddenly, that gate is wide open and current starts to flow. That flow of electricity is enough to flip our transistor switch to the on position. And just like that, the circuit is complete and the fan starts spinning to cool things down. And here is where it gets really clever. The fan is running, so it's cooling down the room, which also cools down the thermistor. As the thermistor gets cooler, its resistance goes back up again. The gate starts to close, the flow of electricity gets cut off, and our transistor switch flips back to off. The fan stops. See, the system regulated itself completely automatically. So, the really crucial thing to understand here is that this isn't just a simple on-off switch. It's a little intelligent system. It senses a change in its environment, it takes an action to correct it, and then it stops once the job is done. It creates its own balance. And it's all thanks to one tiny component that's just responding to a basic law of physics. And once you know what to look for, you realize this simple principle is absolutely everywhere. It's in the thermostat for your heater, it's the safety circuit that keeps your phone battery from overcharging and getting damaged, it's in your car's engine cooling system, and, to bring it all the way back to the beginning, it's inside your refrigerator and, yep, your air conditioner.
So why do we see it so often? Well, because it's just a really elegant solution to a common problem. Thermistors are super cheap, they react almost instantly to temperature changes, they're tiny, they're reliable, and they're incredibly easy for engineers to design into bigger circuits. I mean, they're pretty much the perfect tool for the job. So there you have it. We went all the way from just squeezing a rubber ball to understanding the brains of a smart fan. It's amazing how these really simple physical principles can power such incredible technology all around us. So now that you know the basic idea, how you can make a device that senses the world and reacts to it, what would you automate?